Yep, we're good.
Okay, so
turn the lights on there.
And that we're just gonna those off now.
Nice.
Okay.
Oh, okay.
So today we're going to be talking about iteration in Python, as you can see, and it's very much specific to Python, what we're going to be covering today. So if we take a look at some technical difficulties, right? So let's say we have a list here, right, and we want to loop through it. We obviously know that in C-like languages, this is the kind of syntax you would use for a while loop. So you would set an index variable to 0, and index the list each time you want to do something with it, and then increment the variable. And this structure is pretty much the same as the for loop, where instead of declaring the index variable before the loop, you do it all as part of the for statement. But essentially, these two are the same. What you're doing is getting a number, increasing it, and then indexing the list to do something with it. And this is the output that we produce, obviously. Both work the same way. But this is not very Pythonic, as it were. Obviously, you could translate them directly into Python, like this. The while loop is pretty much the same. The for loop looks a little different. But these are basically translations directly from C syntax into Python. But actually, if you think about it, this is not really a good way to do looping. There is, in the word iteration means to do something repeatedly, to do a process repeatedly. It's doing something with multiple things, basically. Is you have a series of things that you want to do something with. In this case, we're printing out each fruit. But for some reason, we have this extra variable here, I, which means nothing. It's not important to the loop. It's not important to what's going on here. So there is a better way to do this in Python, where you can directly loop through the fruits. Instead of messing with any I, or messing with any index variables, or any incrementation, all you have to do is do for fruit and fruit, print fruit, which basically says that go through this list, and for each item you see in it, print it out. So now we've removed the need for the I, for the index variable, which looks nicer. It's easier to read. It's also more efficient, very slightly, but it is more efficient. Now, looking at Python, there are other things that you can iterate through with this syntax. You can iterate through tuples as well as lists. Obviously, that was a list. You can iterate through strings. So iterating through a string gives you each character one at a time. So if you wanted to print out each character on a different line, you could easily do it like that. You can also iterate through the keys in a dictionary. Okay. So if you had a dictionary and you wanted to iterate through just its keys, you could do it like that. But if you also wanted the values, there's a function, there's a method on dictionaries, .items, and this actually returns a tuple, which you can unroll into two values. So you can iterate through two different items at a time, even if it's coming out of one iterable. And then there's this, which we've all seen before, the range object. And we don't really understand how it works at this point. All we know is that if we want to do for loops as we saw before, you just do for I in range whatever, and it does some magic. So let's dig a little deeper into this. Here is an implementation of range. If you haven't seen objects before, like don't worry about it. Like it's not important to understand how it works. But what you can see is that you initialize it with start, stop, and step. And there's some special methods here, right? There's the iter method and the next method. And the double underscore on the leading and trailing double underscore means that it's a method that's special. So like it's a special name in Python. It has a special function. It's not just any method that the user has declared. So we can see here that what's happening here is the cursor gets set to the start value. Each time the next value is asked for, it increases by a step size. And then it returns that the current value. And if it gets higher than the stop value, it stops iteration. Or it raises the special exception, which is stop iteration. And to understand where these methods come into play, we can dig a little deeper into what happens in a for loop. So this is the output you would get if you ran this function, the myRange function that we defined as in the last slide. Are there any questions up to now? Because I've been going really fast.
No, this is fine.
Okay. So here's what happens in a for loop. You can imagine that when the for loop, in the first line of the for loop, this object is created. It's initialized. Sorry, not even the for loop. Here, when you create this object, you initialize it. You call the init special method with the arguments that you give to the object or to the class name, and that's basically constructing the object. Then we start the iteration for I and x, and that calls the iter method. So the iter method here in our object, all it does is set self.current self.start, which means brings it back to the beginning and returns the same object. So this basically means restart the loop if there was a previous loop running. And then it calls for the next value. It asks the object for a next value. It says, if you have a value to give me, give it, return it. And our the methods that we defined, they give the next value based on increasing the start value by a step each time. And then once it reaches the bottom of the loop, it does it again. It says, give me a new value from your iterable. And once it reaches that exception of stop iteration, the loop ends. So basically all it's doing is asking, it works the same for every single object in Python. It's just asking for the dot underscore underscore next underscore underscore function, which is method, sorry, which always gives it the next value that it's asked for. So now at this point, going back to what we looked at earlier about looping in lists, you would think, why does the range function have to exist when you could just have a list of numbers? Or even better, you could create a function that generates a list for you based on a range. So instead of having that complicated object that we had earlier, you might think that it's quite easy to just create a list range like this, where it creates a list of all these numbers based on the same arguments from my range. So start, stop, and step increases the cursor by step each time and adds it to the list and returns the list. And you can easily iterate through that. You can say the exact same thing and you get the exact same output. So what's the point of using my range here? Why is the range object in Python not just generating a list? Well, it's because in this situation here, what's happening is the object is created, the function is called, and the function now has to generate the entire list. So from 1 to 10, it's not going to take very long. But if your list if you're iterating through like 10 million values, it's going to have to create the entire list of 10 million, which is going to take a lot of space and memory, and then return it. It's also going to take a lot of time to run that function. Whereas here, the only time a new value is generated is when it's asked for. So when the loop asks for the next value, it's returned. And this is called lazy evaluation. The values are only given when they're asked for. And, helpfully enough, Python has a nice shortcut to create iterable objects really easily. These are called generators. So, it looks exactly like a function, except instead of appending to a list, you yield that value. So basically, when the for loop asks for a value, the generator function will yield that value back to the for loop, and the for loop will continue doing whatever it's doing with that value. And then it'll ask it'll ask the generator for another value, and until it comes to another yield statement, it'll run the generator, and then it'll return that value. So it's the same deal. It's the for loop asking the generator for a value, and pausing, then the generator goes and finds a value, gives that back to the for loop, and it's like back and forth until the generator runs out of values to give. So this can be written as a function, just like this function, but instead of appending to a list, you just yield that value, which is basically the same thing. This line here is just, this line represents the fact that you have a value to return. It's the same here. You have a value to yield back to the iterable. So instead of adding it to a list and waiting, you might as well just send it now. So that's what generators are. And it is basically just a shortcut for creating iterable objects. Now, one of the good benefits of generators is dealing with infinite sequences. So here we have a function. It's generating Fibonacci numbers. But as you can see, it's never going to return because there's a while true here. So this function, if you call it, is going to run forever and ever and ever. And if you wanted to go through an infinite list of Fibonacci numbers, this wouldn't work because it would just run out of time. It would go on forever. So what you can do is instead turn it into a generator. Because while it still has a while true, every time it sees a yield statement, it's going to go back to the for loop and let the for loop do what it needs to do with that value. So you could have a for loop for f in gen fib, and it could go through infinite numbers of Fibonacci numbers without having to run out of, without having to store them all in memory and without running out of time. And you'd be able to generate an infinite number of Fibonacci numbers. And that's pretty much it. But there's probably going to be some questions.
That made so much more sense than when you just explained it to me over there one-to-one. I have a quick question about yield. So if you go back to the slide where you've introduced yield to us.
Yeah.
So, you know, if I use the function at the top and I'm returning the list, it will give back to the program the entire list.
Yes.
And then I can do whatever I want with that list once I've got it.
Yeah.
How would I, by using yield in that function, is it actually giving me anything back to the program?
It's giving you one value.
It's only giving me one.
One value. So back here when we broke down the for loop, it will ask the generator for a next value, and it'll receive one value. And it'll do whatever it needs to do with that value and then ask for a new one.
Yeah. But, so go forward again, Murtaza.
Yeah.
Right, so that function at the top left.
Yeah.
Okay, so if I called that function,
yeah,
and I passed it start 0, stop 5, step 1. If I called that function with that and assigned it to a variable of, let's say, x, what would be an x?
So with this function,
yes,
x would be 0, 1, 2, 3, 4. It would be
as a list, absolutely.
Yeah.
So if I did exactly the same thing with the next function, yeah, so I gave it the start,
the generator.
With the generator.
Yeah.
I gave it a 0, I gave it a 5, I gave it a 1.
Yeah.
And I assign the outcome of that, the output of that, to a variable x in my program. What would be an x?
X would be an object. So if it's exactly like doing, if I say, we can do for I in range of something, right? 1. So we know here that range is an iterable object. But similarly, if we had done x equals range 0 and 1, we could have replaced this with x. So it's basically the same with that generator object. If you called this gen range function, that x equals gen range of 0, 5, 1.
Yeah.
If you did print x, you'd get some gibberish about an address because it's an object which doesn't have a string representation. If you tried to add or do any like arithmetic with it, it wouldn't work. If you tried to append to it, it wouldn't work because it's not a list. It's just an object like the range object. And that object happens to be iterable because it defines those special methods. It defines inner and it defines next. So that's all the conditions there are for having an iterable object in Python. So this object will have been created by Python syntactic sugar because of the yield statement. But in reality, it would look something like when we actually wrote the whole function here. It would look more like this. Whereas a generator is just a shortcut to build this for you.
Okay.
So if x is gen range 0, 5, 1, if you wrote for I and x,
yeah,
what would the output be?
Well, that would work. That would go through if you did for I and x, and then just print I. You get 0, 1, 2.
So that runs the generator.
Yeah, because it'll be just like it's the range function or the range object. It's not actually a function.
The thing is, like, if you do x as range, that
Yeah.
range itself, like, is x an object or is x a list?
X would be an object.
Oh, okay.
Object. If you wanted to make x a list, you could list of range like that, and then x would be a list, which is also an object, but it's just a specific kind of object.
I think the thing for me is context of like when I'd use this and why I'd use this. I understand the why now, because like you're saying, if, for example, if you want to do something that's dealing with infinite values and it's generating a list that is infinite, then it's never going to be generated for you to check.
Yeah.
I understand that. But in the same sense, if I wanted to use it to generate Fibonacci sequence and then print out Fibonacci sequence, what would I be printing? So go back to the one with the Fibonacci sequence in it. If it's just created an object of that Fibonacci sequence, where is it? Right, this is the one with the generator.
Yeah.
For f in, okay. So the first one would never work. Oh, I get it. I understand. Sorry, yeah. So it's created an object.
Yeah.
But when you're going so to actually get it to output values from that object, you use the for loop to go through it, and then that print f would be infinite.
Yeah. So it would keep printing.
Yeah, but the previous one would never print in the first place.
It
It was
was
going to
gonna-
create the list in the first place and then iterate through.
Yeah, this would be the output. It would just hang there.
Yes.
Whereas here you get infinite string values.
Okay. Can you? That's great context for this. But can you think of? Have you had to use this anyway?
So I've used a generator in a slightly simpler case where, has anyone heard of the game of life, Conway's Game of Life?
Yes.
So in Conway's life, you have a grid. Let's just simplify it to 3 by 3. And there are certain rules that you have to apply to each cell, each generation of the game. So let's say this is the cell I'm working with here, and I want to implement the game in a way that it checks all the surrounding cells. So what I could do is I could write if x plus 1, y is something, do something, if I make a series of if statements. But an easier way to do it was I created a generator that just yields, so x plus 1, y, and then yield x plus 1, y minus 1. So it would go through them in order. It would return all the adjacent cells of any cell. So this is a good use of a generator because you've created your own iterable object. Like the iteration here is happening on the surrounding cells of any cell. It's good that you've used a generator because you don't have to repeatedly do if statements. And it also means that you could, if you had to do multiple things with surrounding cells, you could use the same generator multiple times without having to rewrite all of the coordinates for the adjacent cells. So that's one example. That doesn't really deal with infinite stuff, but that's more like custom iteration.
Anybody else have any questions about that?
So when you do yield x plus 1 y,
Yeah.
does that just tell you if like the cells to the right of x is alive or dead? Is that what it tells you?
Well, the generator, let's call it gen adjacent, would take 2 arguments, x and y. And it would go through returning the coordinates of all the adjacent cells. So first it would return this cell, and this cell, and this cell, and this cell. Then the calling, wherever this was called from, that would deal with figuring out if the adjacent cells are alive or not.
Within that part where it calls it, wouldn't you still have to implement all the if statements and stuff to check?
But you don't need to do it once. You'd have one check, which is like for cell in let's say color. X and Y. If and then whatever you need to do with that. So you only need to do one if statement. So if it's alive, do this. If it's dead, do this. But then, if you had, for example, in the game of life, first you have to check which cells are alive. So that's going to be one loop. Then you have to populate all the cells, whether they're going to be alive or dead. And then you need to delete all the cells that are dead. So you have to do them in that order. So there's 3 times you're going to have to call this loop. So this generator is going to be used 3 times. Instead of having to write each of these things 3 times, I've only had to type them out once. And it's Good way of minimizing the code.
Any other questions?
Will? Anyone?
No. You explained that really well, Murtaza, and I'm saying in comparison to before, I think the visuals really help. I totally get why I'm using them now. As before, I was like, I wasn't quite sure. That was really good.
Actually, can I have a question?
Yeah.
You know, in the gen fit there,
Yeah.
if you, within the for loop, if you wanted to, let's say, generate the first 100 Fibonacci numbers, would you like need to know the value of the 100th number to like know when to break?
Well, you could adapt this generator.
Well, you have to do it within the generator, not within the, is there no way to do it in the for loop?
You could do it in the for loop. You could say, I mean, then you have to have another for loop with I, or you could. Oh, this is a good point. It's a good. Thanks for bringing that up. So, one thing that people complain about with natural iteration is if I have, actually, should do it on the slide. If you have a list like this, and you wanted to print out the number and the item, how would you do that without using I? Well, how would you do that naturally? How would you do that? So there is a very nice function in Python called enumerate, which takes one iterable as its argument. So if you wanted to iterate through that, you would just do for I and fruit, like we saw with the dictionary keys and values in enumerate fruits. Okay? So if you wanted to generate the first 100 Fibonacci numbers, you could enumerate them and then say when I is greater than 100, stop, or break the loop.
So just to confirm the syntax of that,
Yeah.
in this example with the fruit, you would literally in Python write enumerate bracket fruits because that's the name of your list. Then you'd execute, well, then you'd write the for loop for I fruit. Yeah.
No.
In enumerate. Or do you not
No,
need to
you don't.
enumerate? Okay, gotcha. Yeah, so for I fruit, in enumerate fruits, print fruit, but then what? What would that, would I also have to print
Let's
I
say
as
if you
well?
want if you wanted to print I.
So I could print I comma fruit.
Yeah.
And that would give me the number of, so that would print out, would that print out 0 apple?
Yeah. And if you wanted to only print the first three, you could say if I is 2, break. So that's what you wanted to know, like how you can stop it after a certain number.
Then if you do enumerate on the generator,
Yeah.
how does I work? Because generators aren't indexed, right?
No, they're not. Okay, so that's a good point. So when it takes a list, the enumerate object, you might think that it's actually going through the whole list first and enumerating them. Actually, what it does is it's like a for loop in itself. So it asks for a value. Once it receives that value, it adds a number to it. So when it was using the when you enumerate the Fibonacci generator, right? It's going to receive the first value and enumerate that before returning it to the for loop. And then it's going to also wait for the next value. So it does it as the values are coming rather than all at once. So it doesn't know beforehand how many values are coming or anything.
So you're saying you could do this with the generator or you couldn't?
You could.
Because it is automatically
Because-
built in to the sense that it does have to generate.
It doesn't. So enumerate will not have to generate any more numbers than without enumerate. All it does is it adds an index to that number.
And
So-
because they aren't indexed, that's what that's doing. It is
Yeah.
indexed.
It's indexing them, but without having to know how many there are. So it would work with an infinite sequence
Okay.
because it's not taking the whole list and enumerating it. It's just giving you the same value but with an index of.
But are you saying if you didn't use a generator, it wouldn't do that? Because it would actually create the list, know how many they are, and then enumerate.
It wouldn't know how many there are. It would just keep counting how many it's gotten. So it starts from 0 and goes up.
That's quite useful.
Would you be able to reference an output from a generator? By doing like genfib blah blah, open square brackets 1 or something?
No, you can't do that because that's indexing and you don't know, it's not generated all of them yet.
But if, like, let's say if you do for f and blah blah blah, and once it's reached the fifth value, can you then reference like the first and second value?
No, those are lost as well. So you only keep the current value. and whatever other information the object needs to get the next value. Anything else? Everyone understand this?
I do actually.
Yeah, it's quite simple because once you understand the special methods that get called in special places, it's easy to see how iterable objects work. So, yeah. Okay, I guess that's it then.
Thank you.